In this video I'm going to look at how we can evaluate changes to polymethyl methacrylate that occur as a consequence of being measured by XPS. So the first row in this experiment represents the as received surface, but as the measurement continues, which is just repetitions of carbon 1s, oxygen 1s and valence band, then changes occur, and these are obvious within the carbon 1s. They are also obvious within the oxygen 1s. So there's a certain consistency in these changes that makes us believe that these are genuine changes in the sample and not some sort of errors in the measurement of the sample. If we simply consider the carbon 1s, we can do calculations based on principal component analysis and evaluate how many different changes that we can mathematically determine within these data. So when I press the PCA button, then the data are transformed into abstract spectra or abstract factors, and these abstract factors are gathering the signal information and hopefully partitioning it from the noise information in the data set. So when I look at the first 4 abstract factors that are calculated, then the first one looks like the average spectrum. The second one has peaks that are reminiscent, albeit negative going peaks, of the carbon bonded to oxygen, both double and single bonded. And then we have another that looks like some adjustment. Perhaps this is a shift of some description in the data. And the fourth one looks very much like noise. So in principle, what we ought to be able to do is reproduce all of these data using 3 abstract factors. In fact, if you look here, the relative intensity of these abstract factors, 2 of them really dominate, so that third one is not nearly as important as the first 2. Nevertheless, I will calculate a reproduction of the data using 3 abstract factors. And this means I'm essentially fitting 3 abstract factors to each spectrum and using that fit as the approximation to the data. So when I press the AF3 button, it then calculates a set of spectra, all now with reduced noise compared to the original data. I'll take a copy of the process form of these data, and they've been moved to a different column, and that allows me to then overlay and reset the data back to its raw state. And what I'm comparing is the difference between the PCA corrected and the raw data. And we can see that if I zoom in, it's easier to see that the PCA result has eliminated a significant proportion of noise. This is the background, and we can also see in different parts that the red trace represents the PCA solution, and it certainly has less noise than the original data. Now the reason why I would like less noise in the carbon 1s spectra is because I would like to form different spectra, and these different spectra by their definition will be subtracting 2 spectra, and subtraction tends to amplify noise, so the less noise I have in the data, the better this calculation will be. Now what I'm going to do now is demonstrate that it's possible to extract from data spectral shapes that actually make sense. It's not always going to be the case that this is true, but for these data it is definitely true, and I can demonstrate this by making use of the data set that has progressed to the point that the PMMA looks like it is no longer present within the carbon 1s spectrum. So let me change the experimental variable so that the index for each measurement is available, and if I look at, say, the range from 20 to 60 inclusive, and overlay these in the active tile, we can already see that the amount of double bonded carbon, oxygen is very much reduced. Similarly, this single bond very much reduced, and we've got a range of different intensities somewhere in between the CC and the CH and whatever else has appeared in these data that is unrelated to PMMA. So these are the raw data. I'm using the arrow key and I'm going to step across. So we see in the oxygen 1s there's definitely changes in the oxygen. The valence band, not so obvious, but I've now got the PCA enhanced data for the carbon 1s, and these are in the range 20 to 60 as far as the indices for these individual measurements. So in principle I can apply different spectra to these data, and I should be able to calculate from these data at least two good significant spectral shapes, component spectra, that I ought to be able to fit back to the original data. And if I'm going to be able to fit this back to the original data, I need to have something that looks like PMMA that derives from these data. So when I press the difference button, this calculates the difference between the first and the last in the list that are selected and presents a new file that contains a series of different spectra, which I'll overlay, and you can see there are a vast range of shapes from which I would like to pick out at least one that looks like PMMA. Now I have a good idea of what PMMA ought to look like because the very first measurement should be very close to PMMA. So let's start searching. As we search through this list of different spectra, the first thing you note is that the double bond carbon oxygen peak starts to grow, and that is matched by a single bond oxygen peak, and I'm watching the shape of the spectrum adjusting, and I think that there's an example of a shape that is not dissimilar from PMMA. I'm going to save that one. Now, using the arrow key, the left arrow key, I move back to the column of different spectra, and I'm looking for the complementary spectrum that should be there by virtue of the mathematics of calculating different spectra, and I'm looking for something which is different from PMMA and looks very much like the type of data that is coming out of the measurement towards the end of the experiment. So this is not the beginning of the experiment, and this is not the end of the experiment. These are a set of measurements that were in the middle part of the experiment, and I've now found two shapes. So let's take these two shapes and we will then apply the two shapes to all of the carbon data. So I'm copying to a new file. So these are the raw carbon 1s data, and these are the two shapes that I've calculated from the middle section of the experiment. And to test whether these work for all the data, I'm going to do a least squares analysis, meaning I'm going to fit these component spectra to these carbon 1s spectra that are selected. So I press the button, it tells me that I've got target spectra of 90 and my basis spectra, there are two. The two come from the active tile, the 90 come from the selected, and I say yes. And then the fit has occurred, and I can then look at how well the fit has progressed. Well, now it's not entirely perfect here, but this looks reasonably good across most of the spectral range. So if I start moving down this list, I'm going through the different carbon 1s spectra that were measured as a consequence of the iterative experiment, and I'm looking down this list and I see that the two spectra that I've chosen are doing reasonably well in approximating all of these spectra from the beginning straight through to the end. So the only one where there's some doubt about the fit is the very first one. But what I've managed to do is pick out from a subset of the spectra two spectral shapes that not only fit the subset, but they extrapolate to the beginning of the experiment and they extrapolate beyond that subset to the end of the experiment. So this makes me feel comfortable that I've managed to pick out from a data set two spectral forms that are potentially solutions to the problem of understanding what happens to PMMA when exposed to measurement by XPS.